Hello everyone, this is Mr. Chu over here. I'm sorry I can't be with you today for the lessons, but life must go on, lessons must go on, just that we are having the lesson at different places at about the same time. So today we shall carry on with topic 7.1. There are few sections of 7.1. There is a thing on the spectral lines transition. There's also a portion on the radioactive decay, and lastly, the fundamental forces. So to begin with this spectral lines, I think we need to appreciate why is it such an important thing. The reason why spectral lines are so important is because it is a technique that allows me to understand what is the composition of stars billions of light years away. Imagine being able to understand something very far away without being physically there, just by taking the light from the star, which traveled to us through billions of years, and we can know what is the star made up of. So this technique is really powerful. But what is even more important, the leap in understanding for that the spectral lines offer us is that the energy levels in the atom is quantized. Now, the reason why spectral lines is important is because before the spectral lines era, before it was observed, it was understood that the atom comprises of a nucleus and an electron that goes around. Now, if you understand the electrostatic forces of attraction, which we have gone through in topic 5, the force of attraction is equals to kqq upon r square. Now, what is interesting about this equation is that there is no restriction on the value of r. It can be of any value. There is no restriction. So what this poses, the problem that this poses is that for a charge that is constantly orbiting and constantly accelerating around the nucleus, it should emit EM radiation. And if it emits EM radiation, just like a satellite in a Earth orbit, it will spiral closer and closer towards Earth. Like this one, it will spiral closer and closer towards the nucleus. And no atom should exist because all electrons should stick to the nucleus, so there's no atom at all. And the fact that atoms exist, that you and me exist, to go through this interesting process called IB, the fact that we exist means that atom exists, means that the value of R cannot take any value that it wants. So why is this so, or what's the evidence for that? The idea that it is, or the explanation as to why it must only take specific values has to do with the topic what we're going to learn in topic 12.1. So we KIV that first. Let's assume that we can explain that there is a need for the electrons to only take on specific values of specific orbits. What is the experimental evidence? So the idea over here is that if the electrons can only take specific orbits, therefore specific energy, then there must be experimental evidence to prove it. And this is exactly what I'm going to go through, which is spectral lines. The evidence for the fact that electrons' energy can only take specific values. Therefore, the electrons can only exist in specific orbits. Therefore, this model, it is incomplete. So what is this spectral lines? Very simple experiment that can be done in very poorly equipped lab. All you need is a white light passing through a cool gas. And after passing through the cool gas, it's going to be going through a prism, and then you observe it on the screen. Now, what you observe on the screen is really quite interesting. It's going to be a colored background with dark lines. Now, the color background is nothing interesting because the color background is basically what Newton observed when he passed the sunlight through the prism, and that's what we see. The reason why we see rainbow, because there is a whole spectrum. Now, in rainbow, you don't see a dark lines. I mean, you don't see dark lines appearing, right? So, but over here, because of the cool gas, somehow it does magic to it, and somehow it just causes the dark lines to appear. So, what does the dark lines tell us? What do the dark lines tell us? The dark line tells us that this is really important because it tells us that specific wavelengths are absorbed. And because specific wavelengths are absorbed, and we know that E equals to hc upon lambda. Now, what on earth is this? This is basically, it comes from E equals to hf. Now this is the energy of each light particle. We'll go through in more detail, more extensively in 12.1, topic 12.1, what this means and what's the evidence for this. But for the moment, just take it that light exists as particles, and the energy of each particle is h times f. H is what we call Planck constant, and f is the frequency of light, and that's why it is equal to speed of light divided by wavelength. And since energy of the photon is related to the wavelength, and only specific wavelength absorbed, therefore only specific energies are emitted. And therefore, since only specific energies are emitted from the, or absorbed, by the atoms in the cool gas, we can deduce that the energy levels inside the atoms can only take specific values. So that's why this observation is important, because it is a concrete proof, without doubt, that the energy levels inside the atom is concrete. The same goes for the emission spectrum. So what is this emission spectrum? Now this is something quite interesting, that when energy is absorbed by the cool gas, it doesn't stay there. Nothing in this world loves to be in high energy state. Everything in this world, this is the rule of the universe, loves to go down the energy ladder. So once the atom absorbs the energy from the light, the specific energies from the light, it doesn't keep it within itself. It will re-emit the light. So the light is being re-emitted in all directions. Now this is important. The fact that it is emitted in all directions means that the intensity of the absorbed light emitted in this direction is very weak. And that's why this is dark. So what am I trying to say over here is that the dark lines are dark not because there is entirely no light of that wavelength arriving. There is a very small amount re-emitted, but because it's distributed in all directions, that's why it is dark. It's just like the sunspot in the sun, on the sun. The sunspots are actually very hot. They are just a couple thousand degrees cooler than the surface temperature, which is still very, very hot. But because in relative to the surrounding, it is cooler, so it appears as something black. All right? So this is something you need to know how to explain in exams, how the dark lines, how the absorption spectra shows that energy levels are quantized. And this light emitted over here is what we call the emission spectrum. Because when you pass it through another prism, you're going to see, make a guess what you're going to see. You're going to see colored lines against dark background. Sorry. So colored lines against dark background, because why? Because the energies that absorb over here are re-emitted here. It is a dark background because it doesn't contain all wavelengths. That's why it's only specific wavelengths. All right, so this is basically the theoretical understanding of why this is really important. Now let's go into the atom. So what I'm drawing over here is basically energy levels. So when the electron absorbs the energy, and it can only absorb the energy equivalent to the difference in the energy level. And that's why it can only absorb this, this, or this. And that's why only dark lines appear, because only wavelength corresponding to these energy differences can be absorbed. So energies in the atom, energy levels in the atom are given, energies of the energy levels in an atom, they're given usually in EV. I hope you still remember what is EV. Say, for example, this is 0 EV. This is, say, 13 EV, 13.6 EV, and 13.8 EV. Say, for example, just some fictitious values. Just a recap, 1 EV is equals to 1.6 times 10 to the power minus 19 joules. And therefore, how do we find out what's the wavelength of light that comes in and gets absorbed by this electron? So what you do is, coming back to this equation over here, E equals to hc upon lambda. Hc upon lambda equals to 13 times 1.6 times 10 to the power minus 19 joules. From here, you will be able to find the wavelength. Given that the Planck constant is this value, really, really small. Now, it's really interesting thing that we'll discuss further down. How scientists are able to measure something of this magnitude. If I'm not wrong, I think this is one of the smallest physical quantity that we have in physics. One of the smallest, if not the smallest thing that we usually would handle. So once you work through this, you'll get the wavelength. All right. Likewise, if I were to re-emit the photon, the same calculation follows. Just take this energy minus this. All right. Sometimes they may actually give you the energy levels in negative values. So say, for example, this is negative 13 eV, this is negative 1.2 eV. It's just the reference values that they use. They use probably, in the question, probably the energy at infinity is 0. So anything that is lower will have a negative energy. And what you need to do is exactly the same. All you need to do is take the higher energy value minus the lower energy value, and you end up with a positive E over here. All right, so that's all you need to know for spectral lines and the transition between energy levels. Why are spectral lines important? Because it shows you that energy levels inside the atoms are specific. You need to know the setup, what is observed over here, absorption, emission. All right, and then you need to perform simple calculation like this one for transitions between energy levels, either going up or going down. Sometimes they give you in EV, sometimes they give you in Joule, sometimes they give you in negative EV. But the idea is the same, higher minus lower, then equals to HC upon lambda. All right, so let's go on to the next part of the 7.1, which is radioactive decay. Now, radioactive decay is something that is, or rather decay is something common in our daily life. If you build something that's too high, if a building is too high, too narrow, too thin, what happens is that the building will collapse. Or if you build any structure that is unstable, it will collapse. So anything that's too big, too heavy, it will tend to collapse on itself. And this is exactly what happens in radioactive decay, just that it doesn't happen at the scale of the building, it happens at the scale of the nucleus. So it is very important for you to know that radioactive decay happens in the nucleus. It is in the nucleus, not the atom, not molecules. It is inside the nucleus. Nothing to do with the atom. So what are the processes that the nucleus go through to stabilize itself when it gets too big or unbalanced or improper compositions of neutrons and protons? So these are the three processes it will go through. Alpha. Now, alpha decay is usually something that happens for very heavy nucleus. It involves the emission of a helium nucleus. So from X, A, Z, it goes to A minus 4, Z minus 2, Y plus 4 to helium. This is a helium nucleus, not an atom. So remember, we're all talking about nucleus. Therefore, what you have over here is, since you emit 2 protons and 2 neutrons, we will have 4 lesser over here, 2 lesser over here. Now, it is also something that you need to know that is over here, the alpha decay usually happens for heavy nuclei. So it emits a huge nuclei out of itself to stabilize itself. Now, the other process that nucleus can stabilize itself when it has too many neutrons and too many protons is via this thing called beta decay. Now, beta plus decay, or beta minus, which is the more frequent one, AZ, involves the emission of an electron. This is essentially an electron. But this electron is not from the atom. Again, please be very careful. This electron is from the decay of something inside the nucleus. Now, what exactly decayed to produce this electron? If you compare the A over here, they are the same. Therefore, we can say that the number of neutrons and protons must be the same. However, the proton number increases by 1. So we can deduce that it must be 1 neutron decaying into a proton and an electron. Now, it is discovered in the, it was actually theorized by someone that, there must be something else that is emitted with this, which is called the neutrino. In this case, it's an anti-neutrino. Now, why is it that this person theorized that there must be something that's emitted? Because for alpha decay, and the last one, which is gamma decay, they realized that the energies of the particle that are emitted is actually constant. It's a specific value, very much like your the emission lines and absorption lines. They realized that helium, this alpha bar decay and the gamma decay, which is the last one, is specific. Therefore, this one should be specific as well. However, the energies of this particle emitted is not specific. It takes any values that it wants up to a maximum value. So why is this so? Because if it is emitted from the nucleus, it must obey the same rules. Therefore, the person postulate that there must be another particle such that the energies of this plus this must be a specific value. So let's take it for example. If I have 7 and there's only one variable x, x must be 7. Whereas if I have 7, which is x plus y, I mean x can be 4.1, y can be 2.9, or x can be 1, y can be 7, there are 6. There are infinite number of possibilities, and that's why when you have another particle coming into the equation, the energies of the beta particle need not be specific anymore. It can be shared between the beta particle, which is the electron, and this thing called antineutrino. We'll talk more about this antineutrino and neutrino later on in topic 7.3. Now there is a beta plus decay where you have y plus a now this is the case where you have too many protons. As you can see, one of the proton decays into a what we call an anti-electron, a positron, and a neutrino. So like what I said, we will go through the particle, antiparticle in greater detail in 7.3. But for the moment, you need to be aware why is it that must be a antineutrino or neutrino, because that explains, and it was detected, it explains why the energies of the beta particle is a widespread spread of values rather than specific values. And you need to know how to write equations for alpha, beta minus beta plus decay. Lastly, gamma. Gamma is the simplest of all because it involves not much of a change in terms of the composition. All you need to know is so it goes from an excited state, which is represented by the star, to an unexcited state represented by the one without the star. So that's a process that usually happens after this and this. Because imagine that if you have a table, you rip a table off the chair, you rip a chair off the table, one of the legs off the table. Now what happens is that the table is going to be unstable. Eventually it's going to collapse into a more stable position. This is exactly what happens over here. Initially, when these particles are ripped out or the reaction happens, it is unstable. Then it reconfigures itself, rearranges itself into something more stable. And by emitting, for the case of a table, it collapses, it produces sound energy. So in the case of a nucleus, when it rearranges itself, it produces this thing, which is the gamma photon. So this is basically alpha, beta, and gamma. Now draw up a table to summarize some more information regarding alpha, beta, and gamma. And these are things that you need to know about the nature of alpha, beta, and gamma. Nature, absorption, stop by paper, stop by aluminum foil, stop by a few centimeters of lead. And this one is ionization ability, very strong, moderate, very weak, deflection by fields, When we talk about deflection by fields, it's electric or magnetic. This is deflected slightly, deflected strongly, no deflection. Now let me explain a little bit about this whole table. Now this one we have gone through it. The nature of alpha is helium nucleus, beta is electron or positron, and gamma is an EM spectrum, EM photon. Absorption wise, alpha particles are big, so it transfers energy very rapidly to whatever that it hits. So it has because of the size, it has a very high chance of collision, and therefore it is stopped by a thin piece of paper. So alpha particle is actually quite safe if it is not ingested. Once it's ingested, good luck. So the thing is, it can be stopped by even clothing. Beta particle stopped by aluminium foil. It is more difficult to stop it. It needs something more substance. Gamma photons, they can only be stopped by lead. Now, think about this. Why lead? Why do we want to use lead? If you actually check the density of substances, lead has one of the highest density. Now, what does this mean? It means that there's a high chance of interaction between the photon and the atom because of the high density. So why not use platinum, which is the highest in the world? Because platinum is expensive. Yes. So the thing is, because of the high cost of platinum, it's impossible to use platinum. Now let's take a look at the next one, which is ionization. Because alpha particle is very heavy, in the heaviest among the three, it can easily knock things out of atoms. So that's why it has very strong ionization abilities. It goes by mass, and that's why gamma is the weakest. It's basically a photon, a light particle, not much of mass. In fact, it's mass equivalent, it's not even mass. Alpha particle deflected very slightly by electric and magnetic field because it's heavy. Try pushing a lorry off course. It's difficult, but it's not impossible. Electron very, very light. That's why when you have a field, it deflects very strongly. And that's how you tell the difference between alpha and beta when you look at the deflection of the particles. Gamma, no deflection because it has no charge. In order for electric field and magnetic field to deflect it, it must have charge. So this is basically the characteristics of alpha, beta, and gamma. Now I'm going to go on to the portion about the rate of the decay, because it is very important for us to understand how fast things are decaying. Because if something decays really fast, it means that we are being hit by a lot of radiation in a very short time. So this parameter called the half-life is being coined. Why not 1/3 life? Why not 1/4? 1/4 because it's square of half. 1/3 because I guess it's just a matter that it is nicer to say 1/2 life. So that's by convention. There's no biblical truth. Now, what is half-life? It is the time taken for half the number of undecayed nuclei to decay. So it means if I have a half-life of 5 minutes, it means that if I got this amount of radioactive nuclei, half of it will be decayed in 5 minutes. And then after another 5 minutes, a quarter of it. Why? Because only that half that is remaining will decay. So it's half of half, that's why a quarter. So if we were to draw a block over here, after one half-life, this would have decayed, this undecayed. After another half-life, you will have this decaying. So therefore, you have half of this, half of half, you have 1/4. Therefore, after every one half-life, you have half to the power of n number of half-lives remaining. Now be very careful. Even though you have half to the power n, whatever that is decayed is not half to the power n. Say for example, this one is 0 decayed, this is half decayed, but this is not 1/4, it is 3/4 decayed. So you need to be very careful what the question is asking. Does the question ask for the number of decayed nuclei or the number of undecayed nuclei? Undecayed, decayed. So be very mindful about this because both options can be in the MCQ. So just open your eyes wide what they're asking for. Now, How about the case where it is in between 1.5 half-lives? This is something that we will touch on in 12.1 and 2. So this is basically the very basic understanding of half-life. And therefore, if you were to plot the number of particles if you plot the number of particles remaining undecayed with time, you're going to find that it goes down like this. After 1 half-life, it is n0 upon 2. After 2 half-lives, it is going to be n0 upon 4. It's going to be an exponential. And why exponential? I'll show it to you the next lesson next few lessons when we go on to 12.1. However, what I want to show you is sometimes you can actually get a situation like this. Now, when you get a situation like this where it decays to a value which is, okay, probably this one, if it is this one, then you should actually talk about activity, which is the decay rate. Now, what exactly is activity? Activity is basically the detected radiation from the substance, the undecayed substance. For every particle that decays, you throw out either alpha, beta, or gamma. So therefore, we can say that A is proportional to N. Like what I said, I'll go into greater details into the mathematical understanding and how this leads to this exponential graph later. But for the moment, let's take it that activity is proportional to N. That the number of nuclei present will determine the rate at which you detect the alpha and beta. And it's directly proportional. And why is it directly proportional? Something to do with probability. We'll discuss more about this. So when you detect the activity, it goes down to a non-zero value. Not N, it's activity, the rate of decay. So why is this so? It means that in this case, you will have this thing called the background radiation. Now, the background radiation can be due to minerals in the ground. It can be due to cosmic radiation. When I went to CERN, it was you can witness for yourselves when they built the bubble chamber. It's a lot of radiation coming from the sky, amazing amount, really really shocking. So there is actually a lot of background radiation, especially if you go up in a plane and fly up high. There's a lot more radiation. So what is interesting about this is that then how do you find the half-life over here? Over here, if you have N, which is the number of undecayed nuclei, and then it decays to 0, then you just need to halve it and then quarter it, and then you can find 2 values of half-life, and then you can do your averaging. However, if you have this thing over here which decays to a non-zero value, you cannot simply just take, if this is A0, you cannot simply take A0 upon 2 and read this as half-life. So what should you do? Let's go through the sequence, yeah? So, activity, original is equals, original detected is equals to A0. And activity, original, actual is equals to A0 minus ABG. So this is taking away the background radiation from here. So that's the actual one without the background radiation, purely due to the sample. Activity after 1 half-life, actual, is A0 minus ABG divided by 2. So after 1 half-life, the sample's count rate will drop to half. But this is not what you detect because the background radiation is everywhere. So activity after 1 half-life detected is equals to A0 minus ABG divided by 2 plus ABG, which is going to be A0 plus ABG divided by 2. So this is what you do. Say if this is 120, this is 30. What you do is you take 120 plus 30, 150 divided by 2, 75. You read off 75, not 60. 75, not 60. So you have to be very careful, check whether it decays to 0. If it doesn't, this is what you should follow to find the half-life from the exponential decay graph. Alright, Ken? So lastly, I would like to go through the forces that is responsible for all this decay. We will not go too deep into it, but just a basic understanding. Like what I said, if you have a building that is too high, it will fall down. What's the force responsible for the decay? If it is too high, gravitational force. So there must be forces responsible for pulling things down, causing it to decay. So for these forces inside the nucleus, there are 4 of them. It's nuclear strong force, EM force, nuclear weak force, and gravitational force. So this is in the order of decreasing strength. Nuclear strong force the strongest, EM second, weak force the third, and then gravitational force the last. These forces are the ones responsible for things that happens inside the nucleus and things that happens between nucleus, things that happens between masses. So these are talking about forces at different scale in different situation. Now we'll talk about how these forces are transmitted in the next 2 topics down, which is 7.3 and 12.12. So with this, I'll end the lesson for this portion 7.1. Just a quick run through. We have gone through spectral lines transition, how spectral lines shows that the atom has specific energy values, how to perform simple calculation, radioactive decay, the nature of the different particles, and the equation writing. Half-life, why is it important, and what happens after every half-life, what is decayed, what is remaining, you need to know this. Background radiation, the impact on the graph, how do you know that there's background radiation, and what's the necessary steps to calculate the half-life, to find out the half-life if there's background radiation. Lastly, fundamental forces. For fundamental forces, you need to know their sequence in order of decreasing or increasing strength. With this, thank you, have a good day.